Um,
So good afternoon. I'm Martial Haeffelin from IPSL in Paris, and I'm going to talk to you about Doppler cloud radars. We are interested in studying the formation evolution of clouds, which involve multiple and complex processes, and in particular, the evolution of hydrometeors that come in many sizes and shapes. These can be observed both from in situ measurements on board aircrafts or balloons, but also using remote sensing from space and from the ground and using Doppler cloud radars. So what are these Doppler cloud radars? They are emitting millimeter waves and getting a signal backscattered from hydrometeors through a Rayleigh scattering regimes. And we use principally two frequencies, 35 and 95 gigahertz in the Ka and W band, because those are two frequencies at which the atmospheric transmission is maximum when we consider different gases such as water vapor and oxygen. And at these frequencies, the main attenuation is actually come from the larger precipitation droplets. So the quantities that we want to measure are the reflectivity of these hydrometeors, as well as their Doppler velocity. The reflectivity is not measured directly. What we measure is actually the power that is received back to the radar through the echo of the emitted signal echoed by the hydrometeors. To retrieve the reflectivity, we have to add to this received power the amount of signal that has been attenuated by the atmosphere in both ways. The effect also for the distance between the radar and the hydrometeors, and also a calibration constant that need to be determined. And that can be determined from targets, for instance, that have a known reflectivity. There are several types of cloud radars, typically operating either using continuous waves that have been to be encoded using, for instance, frequency modulation, or pulsed waves where each pulse is independent from each other. Cloud radars come also in single or double polarization, which allows to give information on the hydrometeor shapes, and also are either in a configuration vertically pointing to sound the atmosphere above the radar, or with scanning capabilities to get a more volume view of the atmosphere. So because of these different capabilities, power, the data quality can be different, and also the size and weight of the instrument can vary significantly. So we have here three manufacturers, RPG and Modem, that propose frequency modulated continuous wave systems, predominantly at 94 gigahertz, and then the Metec that provides pulsed radar at 35 gigahertz. Now, from these measurements, we can use several of the measured properties to actually identify and classify the hydrometeors in the atmosphere. So for instance, using reflectivity, we have here time and height cross sections. We can see that there is a wide range of reflectivity depending on the amount and size of hydrometeors in the atmosphere, from ice clouds to liquid clouds. Also, the Doppler velocity allows us to distinguish, for instance, the precipitating regime of the cloud, so the rain, and also updrafts and downdrafts in the clouds. The depolarization ratio can help us to look at the shape of the hydrometeors, and in particular the melting layer inside the clouds, and then the turbulence, so the spectral width in the Doppler spectra can also help us to identify areas of higher turbulence, more variance, like in the rain. So all these parameters are used to derive target classification. Next, to access the cloud microphysics, we have to know that the reflectivity of a volume is actually proportional to the 6th power of the size of the hydrometeors. And the quantity that we're interested in, for instance, like the liquid water content itself, is proportional to the 3rd power of the size of the hydrometeor. So the relationship between reflectivity and liquid water content actually depend on the size distribution. As you can see on this figure, the relationship between the two variables is different for non-precipitating clouds, which have typically smaller droplets, precipitating clouds that include larger droplets, and then the raindrops, which is yet another size distribution regime. Other advanced products that can be derived from cloud radar measurements are, for instance, for fog monitoring. What we're seeing here, again, the time height cross-section of the reflectivity, the top left, we will have vertical profile of this reflectivity, giving us some information about liquid water content and droplet size. And in particular, also, we can infer the evolution of the fog top height, which is an interesting indicator for fog dissipation. Also, when we have scanning cloud radars, then in addition to reflectivity and vertical velocity, we can then infer some information about the wind inside the clouds, wind speed and direction, and for instance, retrieve wind shear, an important wind shear in some cloud situation. Finally, the network that we have currently in Europe consists of about 20 cloud radars, and they are mostly operated by academic stakeholders, university research centers. There is, however, a potential for further development of this network, in particular for fog applications that could involve a more operational stakeholders such as airports. So I thank you for your attention. I'll be happy to answer some questions. I don't know if there's any questions.
There is one comment on the pad from Emiliano Orlandi. Says that RPG is also producing and selling frequency modulated continuous wave radar systems at 94 and 35 gigahertz and also combined.
Yes, so I did mention the 94 gigahertz frequency, and yes, there is now also a new product where this instrument is also available at 35 gigahertz and the combination of both. Yes.